I have a challenge. Find a number on the number line that when multiplied by itself will become negative. Did you find one? Chances are you didn't, because a positive number multiplied by itself gives a positive number, and a negative number multiplied by itself gives a positive number as well. The only other number we know is 0, which multiplied by itself gives 0, not a negative number. So it seems like no other number exists. Mathematicians ran into a similar problem when they were trying to solve a specific kind of equation shown here, an example of what's called a depressed cubic equation. Though there were already formulae for how to solve this equation, the solutions involved square roots of negative numbers, which didn't make any sense. Yet, adding them gave the number 4, which is also a solution, one they couldn't find otherwise. So there must be more to this, right? Well, why don't we make a number, I, where I equals the square root of negative 1? We don't know whether these numbers are real, so let's call them imaginary numbers. Thus, the square root of any negative number should be imaginary, right? The square root of negative 4 is root 4 times root negative 1, which is 2i. Generalizing it, the square root of a negative a is root a times I. Let's say we have the number 1 plus I. Let's call it a complex number. We can't simplify it, but can we work with it? It turns out you can. All the regular rules of algebra apply like normal. 1 plus 2i plus 1 minus I gives 2 plus I, the same as if that I was an x. Complex numbers always have two unmixable components, so how can we visualize them on the number line? Trick question, you can't. But what you can do is visualize them on a number plane, the horizontal axis representing the real part and the vertical the imaginary part. For example, the number 1 would still be here on the number line, but the number 1 plus I would be 1 unit above it because there is one I. Mathematicians call this plane the Argand plane, and this coordinate system is called the rectangular coordinates. However, there are other systems of coordinates you can use. One is the polar coordinate system. Instead of depicting real and imaginary coordinates, you find the distance from 0 and the angle to the horizontal, similar to compass bearings, for example, hiking 2 kilometers northwest. We write this number either as r times cosine theta plus I sine theta, because of our trigonometric rules here, which allow us to convert super easily, or r cis theta, which is an abbreviation. But in the 1740s, Swiss mathematician Leonhard Euler proved this incredibly powerful identity. Polar coordinates can be written as a singular number, r times e to the power of I theta. This is super important because multiplying, dividing, and even taking the power of any complex number to another number becomes easier, since we can just apply index laws. This is also where the famous formula e to the power of I pi equals negative 1 originates. This relationship is also important because exponential form is much more favorable when using calculus, which is essential to several areas in science, mathematics, and engineering, since you can find the slope or area of an exponential function much more easily as compared to a sine or cosine function. For this reason, complex numbers are incredibly useful to scientists and engineers alike, even if they aren't physically measurable. For example, pretend that you're spinning a yo-yo at a constant angular speed. Radians is a unit for an angle, like the unit degrees, and angular speed represents just how fast that angle changes per second. And let's just say that the rope's length is r meters long. Then, if you treat one axis as the real axis and the other as imaginary, you can say that the yo-yo is moving according to the formula SRE I omega t, where omega is the angular speed and r is the radius from the center. Using calculus, we can find that the velocity is I omega times the position. This is important because the I, which can be written as EI pi on 2, multiplying the position shows that the velocity is always perpendicular to the displacement from the origin. Finding the magnitude of velocity results in V equals omega times r, a formula that is useful to physicists. If we find the acceleration using calculus, we get the acceleration is minus omega squared multiplied by the same position complex vector we saw before. This shows us that the acceleration always points towards the circle's center, and it is for this reason physicists call this kind of motion centripetal motion, where centripetal means center seeking. This makes sense because as you're spinning a yo-yo, the only force that is keeping it in circular motion is the tension force of the rope. Complex analysis, as it's called, isn't just limited to Newtonian mechanics. Electrical engineers also utilize complex numbers to measure the impedance of alternating current within a wire. An alternating current is just a current that flips direction regularly, 50 times a second in most countries. And impedance is the opposition to the flow of electricity, which is kind of like friction in a wire. Using complex numbers allows for calculating the components of impedance much more easily, especially because of complex numbers' wave and exponential duality. These examples show why complex numbers are useful, but we don't actually need them for the problems to make sense, right? Well, there are multiple instances where certain phenomena only make sense when you use the imaginary unit. One example is Schrodinger's wave equation, shown here, which describes the probability that you'll find a particle in a given location. It stems from two quantum physics concepts: the Heisenberg or uncertainty principle, where you cannot know the position and momentum of any particle exactly, and wave particle duality, where things like electrons and photons act both as a wave and a particle, but never at the same time. Although it looks incredibly complicated, there are two things we can look at. In blue is the wave function, which describes the probability of finding, for example, an electron at a given location. In red is the imaginary unit, which is essential because this equation only works when waves and exponentials can be treated as the same as each other, especially from a calculus perspective. As it happens, the solution is a complex wave, which obviously cannot be described using just real numbers. The fact is, whether we accept it or not, complex numbers are an integral part of science, technology, engineering, and mathematics, STEM. And even if complex analysis is not required to understand certain phenomena, there are still many aspects of physics and mathematics that we cannot hope to analyze without it. But the field of complex mathematics is by no means complete, or the only number system in existence. Ultimately, complex numbers as a whole have allowed us to venture forth into the realms of physics and mathematics further than we could have dreamt of accessing otherwise. Thank you for watching my video, and I hope you enjoyed learning about complex numbers.